Welcome back to the course on fluorescence spectroscopy, uh, describing the basic principles and the biomedical applications. This is part 6, which is going to be on solvent and environmental effects on fluorescence. This is really a very complicated topic because there are so many possible things that can affect fluorescence, so many types of interactions. Uh, for some of the molecules, we might already know how they behave, and for others, we don't. So really, we have no general theory to describe uh, the effects of environment on fluorescence. The only theory we have is really empirical. It's the things that we've observed in the past. So the goal of this lecture is not to describe everything because we could write books about that, but rather to obtain a general understanding of spectral changes that occur with changes in solvent or changes in the probe environment. Here are just some of the types of interactions that can affect fluorescence. The one we're going to talk about first today is solvent polarity, but other things that can affect an emission spectrum are hydrogen bonding, charge shift effects. Probes can interact with themselves. You can have conformational changes or structural changes of the probe. And then the ubiquitous non-radiative rates that take the fluorophore to the ground state by pathways that we don't know anything about. And these probably affect a lot of the changes we see, but we don't know how to calculate them. So I found this on the web. Here's a general schematic for spectral relaxation, and I thought it was a good one to start with. So we start with the fluorophore in the ground state, and fluorophores in the ground state generally have a smaller dipole moment than do fluorophores in the excited state. So you have a fluorophore in the ground state with a random distribution of solvent molecules around it. They're positive on one side, negative on the other. And when that molecule goes to the excited state, it's an instantaneous transition, and the solvent distribution is exactly the same as it was in the ground state, because there's been no change for no time for anything to happen. Then, since the molecule hangs around for on the order of nanoseconds, the solvent can reorient around this new excited state dipole, as you can see by the change in the direction of these dipolar molecules around that fluorophore. That causes an energy shift, which can be, if you knew everything about the fluorophore, I guess you could calculate it from electrodynamics, but it's not generally done. And then it returns to the ground state. And when it goes to the ground state, many times this effect is ignored and forgotten. But when the fluorophore returns to the ground state, it still has the excited state distribution of dipoles around it, and that has to then relax to the equilibrium excited state. As a general rule, if the fluorophores, they increase their dipole moment in the excited state. If that happens, or the distribution of electric charges change, and it's in a polar solvent, there will always be a red shifted spectra. That's from the basic physics. I guess it doesn't always turn out that way, but as a general rule, this has to be true. So let's look at some examples of solvent-sensitive fluorophores. We'll look at this molecule here. It uses an acronym DOS. You might notice there's a nitrogen on one side and a carbonyl on the other, which means an electron donor on one side, electron donor on the acceptor. If you put this in different solvents ranging from cyclohexane to butanol, you get an enormous shift in the emission spectra. And that's because in the most polar solvent, the charge shifted state is stabilized by the solvent reorientation. If you put it in a completely nonpolar solvent, hexane or cyclohexane, there's nothing to decrease the energy of that charge distribution in the excited state, so it doesn't shift to longer wavelengths. So this is, I guess, one of the most solvent-sensitive fluorophores. We have noticed these are normalized emission spectra. We haven't corrected them for any intensity change that might have occurred. Here is a common effect that is observed with many fluorophores. You might remember from one of the previous lectures we were talking about NADH and how NADH is self-quenched by the collisions of the adenine with the NADH nicotinamide end, and that decreases the lifetime in the free state, and the lifetime goes up in the bound space because it can't collide any longer. That's not exactly what happens, but many fluorophores of this class, TNS or ANS, which is the same thing without the methyl group, will display very low fluorescence in water and very bright fluorescence when bound to a protein. For this particular spectrum, it was apomyoglobin, where the nonpolar site is where the heme used to be, and the TNS binds into that nonpolar site, and the emission intensity goes way up. And we have the experimental bottles here to show you the no fluorescence from the HSA because it's a longer wavelength, not absorbed, tinier amount of fluorescence from the TNS, and a huge, very bright fluorescence when they're mixed together. This is one of the earliest biophysics experiments that were done. This was, maybe other people have done it, but one of the first reports of this type of effect was done by my mentor, Professor Gregorio Weber, back in 1966, where he observed an increase in fluorescence of a molecule just like this when it bound to human serum albumin. So in a case like this, you can measure the amount of bound fluorophore or the binding constant just by looking at the fluorescence, and you don't have to worry about the unbound fluorophore. This isn't always the case, so you can't say that whenever you have a bound fluorophore, you don't have to worry about the free fluorophore. So as an example here, we have protein, which is either in the buffer solution, which is here, or which is bound to bovine serum albumin, which is here. It's fluorescent at blue shifts when it binds to the serum albumin because there's a hydrophobic area there, so it thinks it's in something more like hexane or cyclohexane than in water. But you can't just arbitrarily assume that the fluorescence you see is from the bound form, because the free form can also emit. I thought this was a great example, and I even spent some time to look for an example of a phase transition on the web. Excuse me. When you get phospholipids, you make phospholipid vesicles. You find they undergo phase transitions, especially if they're unsaturated phospholipids. So below the phase transition, they'll be in a well-ordered state. Above the phase transition temperature, the lipid bilayer will be in a disordered shape. And this phase transition could be investigated with a probe like Prodan because it displayed a very large shift as the membrane went from the solid state to the liquid state. And of course, that's because of this this charge shift sensitive protein type molecule. I think they used a protein with a long alkyl chain in this experiment to make sure that it bound to the lipid bilayer. The large spectral change allows you to even do imaging experiments. So this is an experiment in which the localization of the phase transition was measured from the emission spectra, where it was collected at different points. And this is a phospholipid vesicle, which is seen from the side, so you only see the outer surface, probably confocal. And it was looked at different temperatures, and at the color coding seems a little bit backwards, but the authors of this paper decided to define the generalized polarizability as the difference between the blue and the red emission intensities divided by the sum of those emission intensities, and they call that the generalized polarization. So from that, they can see the phase transition in the middle of the phase transition, where the half of the vesicle is in one state and half is in another state, and then up to the higher temperature where the phase transition has occurred completely. This was a very good idea, but don't get it mixed up with polarization or anisotropy, because we'll discuss that in a different lecture. And I think the authors used this generalized polarization because it would be difficult to measure the fluorescence anisotropy with the optical geometry that they had, so they defined something more convenient. Unfortunately, there is no general theory that can describe the spectral shifts or the Stokes shifts that we've been observing. The best that's been done is to consider a spherical fluorophore, and of course they're not spherical, and you put it into a medium that has some dielectric constant, and you calculate the energy of that sphere when it has different dipole moments. So, in the ground state, it's going to have a different dipole moment than in the excited state. And I haven't written down the equations for the reactive fields, but the energies depend on the reactive fields of the solvent. And I've put that together in the next slide so we can track everything that's going on here. So this isn't going to be the derivation of the Lippert equation, which is the most widely used equation when you're looking at Stokes shift. So you start with the ground state fluorophore, randomly distributed dipoles around it, go to the excited state. Nothing happens to the dipoles, but you're in the excited state. The solvent relaxes, and you go with the oriented system, and then when it emits, it's in that system, the excited state, solvent orientation, and then it goes back to the equilibrium position. And this exact model was used by Professor Lippert to describe what is called the Lippert equation. And it looks pretty messy, but it's not quite as bad. What they have here is the difference in energy between the absorption and the fluorescence. So this is common in physics, instead of using the wavelength to use the energy of the photon. There's a term here, which is the difference in the dipole moments between the excited state and the ground state. And then we have this troubling term here, which is the radius of the fluorophore, or the cavity that the fluorophore is in. But since we know the fluorophores are non-spherical, cavities can't be spherical, so it's not going to apply perfectly all the time. This is perhaps the most confusing term for everyone. Why do we use this expression, which is called the orientation polarizability? The reason it's used is because it accounts for two effects. This part is the dielectric constant. that's really a low frequency response. You put a fluid between two metal sheets and you see what charge builds up on it, and then you measure the dielectric constant. That's a static measurement which allows the molecules to reorient as much as they want in that particular electric field. But this one is the refractive index, or a function of the refractive index. And this accounts for the instantaneous change in the field around the fluorophore due to the refractive index, because that's basically at the frequency of light. I've even had a very famous professor call me one time, and he said, "Joe, what's going on here? I can't understand this because these values are near 20 and these values are near 1. And we all know that the dielectric constant should be n squared, but they don't tell you that they're referring to two very different measurements." Well, unfortunately, this is the only theory we have, so we have no general theory, so we'll use what we could go with. So let's look at the solvent sensitivity of some ANS, TNS type molecules. We have two different molecules here, a smaller one and a larger one. Stokes shift is here in frequency terms. The orientation polarizability is here along the x-axis, and you can calculate all you can calculate is the difference in the dipole moment between the excited state and the ground state. So from the slope of the curve, you can calculate that dipole difference. I might have these in the reverse direction here, but I don't think that matters for consideration. But what you can see is the larger molecule has the larger slope, which means it has the higher change in dipole moment in the excited state, which is exactly what you would expect. It is possible in some cases, not always, but in some cases, you can design the solvent sensitivity into the fluorophore. And one group made this interesting series of molecules that starts with really no reason for there to be any electron shift in the excited state, down to this molecule, which has an amino on one side and a sulfonamide on the other side. So of course in the excited state, you expect there to be an electron transfer. So you expect the solvent sensitivity of the fluorophore to increase in this direction. So if we just look at the solvent sensitivity of that molecule, you can see that it is highly solvent sensitive. This is called the Dipoxyl series. We don't see as many results from them, but they seem to be a very useful class of probes to me. I guess a lot of derivatives, or conjugatable derivatives, are not available. But you can see as you go down the chart here, the absorption shifts to longer wavelengths and the emission shifts to longer wavelengths because of the chance of an electron transfer in the excited state. Temperature effects. This is done in propylene glycol. The reason this is done in propylene glycol is because it gets very viscous when you cool it down, and it even turns into a solid glass-like state. But if you take any fluorophore, tryptophan here, make it cooler and cooler, it shifts to the blue. Same thing with this Pac-Man derivative over here. As you cool it down, the spectrum shifts to the blue, which is just like shifting to a less polar solvent. This is because we haven't considered this yet, but there's a certain rate for the solvent reorientation, and we're going to consider that rate of reorientation in a later lecture. But when you're in the cold state like this, where it's very viscous, the solvent molecules can't reorient and the spectra shift to the blue. Now we're going to start shifting between different solvent effects because, solvent polarity is what everyone considers, but there are other effects, and the one we're going to consider right now is hydrogen bonding, which it can cause a specific solvent effect. And in the Lippert equation we showed you, it doesn't consider hydrogen bonding. It's only looking at really macroscopic constants for the solvent, so there's no consideration of hydrogen bonding. But hydrogen bonding can be very important for the spectral shifts of any fluorophore. And I've chosen one here that shows both specific and general solvent effects. I guess this is a cyclohexane solvent. For this 2AN molecule, if you put it in cyclohexane, it has a blue shifted emission. And as you put in very small amounts of ethanol, it goes over to a long wavelength state. And these are really two different effects. This initial shift in the first two spectra are where you're having hydrogen bonding interaction with the 2AN. And after that, you shift to general effects where you're just making the solvent into more and more ethanol-like. And you have a general shift towards longer wavelengths. So if you look at a number of molecules, considering the Lippert equation, you find that effect that I just showed you as a specific effect shows up when you're trying to calculate the Stokes shift of the dipole moments. So here, once again, we have the Stokes shifts in energy units and the orientation polarizability. If you look at different solvents along that scale, everything fits unless you have a product solvent. So these particular methanol, propanol, and formamide have the possibility of forming hydrogen bonds. So that's where the Lippert equation fails when you get to the product molecules. And I don't know why I always like this example, but I've used it several times. It's a molecule that shows very stark both specific and general effects. In general, the ground states are not very much affected by those small changes in polarity because you don't have any of these increased dipole moments yet. But the moment you start titrating in a little bit of polar solvent, not only do you lose the structure of the original spectrum, which is here in the polar solvent, but the emission intensity goes up and it loses all that structure. So it's like a different molecule that is emitting. And this can be shown in a different way. I'll describe this one first. Here we just have the percent of polar solvent and the emission maxima. And this makes more sense to an experimentalist because these are the way you usually think about the way you collect data. So here, right at the beginning, where you're adding a small amount of polar solvent, there's a very large shift in emission wavelength because of the hydrogen bonding effect. Once you get to higher and higher percentages of the polar solvent, you're seeing the general solvent effects, which shift the wavelength more slowly to longer wavelengths. And if you did this experiment where you compare non-product and product solvents, you find the same thing as deviations with the product solvents, but I like this side better because it just matches immediately what you're observing from your spectrofluorometer. Okay, we're going to change to another type of excited state interaction, and these is just charge shift probes. I only have one example of this, but some probes can show a complete charge separation of charges in the excited state. And the example that we have for this is a both-dipping molecule with a aniline or dimethyl unit attached to it, makes this a strongly electron donating structure. So if you put this in different solvents, if you put it into a nonpolar solvent, the charge shift doesn't have any effect because there's no solvent to relax. As you put it in more polar solvents, you begin to see a longer wavelength emission, and that's the emission from the charge shifted state, which doesn't have a chance to form in the absence of a polar solvent. And like I said, we're going to be shifting between interactions, and I actually like this next set of slides. So we're going to talk about excimers, which is a form of probe-probe interaction. And an excimer is a complex of two identical molecules. The first example of an excimer is a really fun experiment to do in the lab. You take some pyrene, put it in a nonpolar solvent, and increase the concentration. And it's not very, the shift isn't very visible to the eye in this type of presentation. But as you increase the pyrene concentration, there's a profound shift in the emission spectrum, because at the low concentrations you just have this structured symmetrical polycyclic aromatic which has a structured emission, but as the concentration gets higher, the two molecules diffuse together and they actually form a charge transfer complex, which is called this excimer. And the excimer has this long emission maxima. The reason this works so well, other polynuclear aromatics can do this, but you don't see it because they don't have time to diffuse and contact one another. Pyrene has a very long lifetime on the order of 400 nanoseconds. Because of that, it has a long time to diffuse and to form excimers. Here's a real, believe it or not, a biochemical example of an excimer formation. This was done with this particular phospholipid derivative down here, where the pyrene was attached to an alkyl side chain. It was placed in, some small quantity, maybe 1 per 100 phospholipids, into a phospholipid vesicle. And it was examined at different temperatures, below the phase transition and above the phase transition. So below the phase transition at 4 degrees, this molecule cannot diffuse very far, and the emission is dominated by the pyrene emission itself without forming an excimer. If you heat up the phospholipid vesicles, it all changes to excimer emission, because the lipids can diffuse laterally very rapid in the liquid phase. And given the long lifetime of the pyrene, it's shorter in this case because it's derivatized, but it's still over 100 nanoseconds, plenty of time to diffuse and form excimers. This is a great experiment. I've always liked this one. The goal of this experiment is to detect this unlabeled target 30 tumor, 32 nucleotides. And the way it was detected was probes were made for each half of the 30 tumor and I shouldn't say that word because it sounds like the biological tumor, but I don't mean that, so I'll just call it an oligomer. And it was reasoned that if this oligomer were present, they would bind closely together and form an excimer. So these two molecules were synthesized with pyrene attached to them, and they looked at what happened to the pyrene emission as they added the oligomer to it, and it was really quite beautiful. In the absence of the target oligomer, it's all the monomeric structured pyrene emission. As they increase the concentration of the oligomer, you see more and more excimer formation, as is indicated over here. And I didn't want to put in too many details, but this was found to be very sensitive to even one nucleotide change in this oligomer. And I'll remind you of something that I've said in previous lectures. One of the previous lectures, when you're doing an experiment like this, you leave all the instrumental conditions alone. If you don't, you won't have any way to compare the relative intensities in the different places. So, exciteplex. An exciteplex is a complex of two different molecules. The classic exciteplex has always been the anthracene and diethyl aminobenzene, or let's see, diethylaniline. When you just have the anthracene in solution, you see its emission. You put in this amino-containing molecule, and you see the exciteplex emission. It's also a charge transfer complex. The point I wanted to make here is that the exciteplex is not always observable. It's observable in this case because we chose this, but in many cases the excitaplexes are not observable, and it just looks like a quenching reaction. And I thought, well, I had to find an example of an exciteplex for you. So I thought this one was as good as any. These days, excitaplexes are used in making organic light-emitting diodes, and the organic light-emitting diodes are in all of the optical displays that you look at, including your television. So turns out to be pretty important. They must be pretty darn photostable to last so long. So that is the end of part 6, and there's something we haven't considered yet, and we're going to do that in another lecture. In all of these slides that I've shown you, we haven't considered the time at which the solvent reorients, because there's going to be a solvent reorientation time, and if you have a fluorophore bound to a biomolecule, the biomolecule doesn't flex that fast, so you wind up with flexings of the biomolecule during the lifetime of the excited state. So now you have emission at the same time the reorientation is going on, and they're going to be called time-resolved emission spectra, which we'll talk about in the next lecture. So I thank you very much for your attention, and we'll see you next time.